Hello everyone and welcome back. Today I'm gonna talk about a model that I have developed for black holes. So according to Einstein's general theory of relativity, space and time are quantities that run freely from one infinitum to another, and they are infinitely differentiable and continuous over a smooth manifold, meaning that they are like sheets of paper that are so smooth that you can't actually see any defects on it. But is this an accurate description of reality? Well, no. According to quantum mechanics, we know that space and time, like all other entities, needs to be quantized, and they need to obey Heisenberg's uncertainty principle, meaning that space and time won't be like this sheet of paper, but like the rain outside today, it is like the fluctuating body. So when you look closely at a quantum level to your manifold, it needs to fluctuate space and time continuously. But how can we model this in general relativity? Well, the way to do that is to introduce a concept known as dispersion. Well, what is dispersion? Well, in classical optics, you might probably heard of this. In classical optics, when a light ray passes through a medium, what happens is that generally a photon cannot constitute its own shape over the distance, because generally the refractive index profile is dependent on the frequency of the light ray. And since light ray consists of a spectral decomposition, meaning that it is a superposition of different frequency components, then different components of the internal constitution of the light ray will propagate in different speeds, meaning that the shape of the light ray that you first introduce to the system will distort over the distance. So this can actually be happened in general relativity. So what we propose here is that space and time actually get distorted when you look closely over the manifold. And this dispersive effects of classical general relativity should be dominant when quantum effects get stronger. And in which places do the quantum effects dominate over gravitational effects? Well, you are right, in a singularity. A singularity is the point of space-time that is so dense where nothing can actually exist there, because the volume of any entity should be zero, because space basically becomes like a zero element. So there isn't any, so it's like we have a we are all four-dimensional entities. We see our space, we define, for example, a place, an event on reality by referencing three spatial dimensions and one temporal dimension. And what I'm saying is that at the point of singularity, the spatial dimensions vanish. So you don't have any coordinate system to reference the position of that point. Meaning that that point does not exist in a spatial dimension. Meaning that that point, poof, vanish. So singularities are not sensible objects. And many physicists believe that singularities shouldn't be plausible, meaning that there should be some quantum effects that prevents the formation of singularities. So many of you out there probably know that people have captured the photo of a black hole. So you might say, well, Eren, a black hole exists. So how can you say that a singularity does not exist? Well, I say that singularity does not exist, but black hole doesn't only consist of a singularity. It has something called an event horizon. An event horizon is something sensible, and it actually encodes the knowledge about an event horizon is encoded in our metric, which a metric is like the basic building block in general relativity. So this singularity is encoded in our metric, and this singularity, let's say singularity that corresponds to the event horizon, as we call the Schwarzschild radius, can be bypassed using a different coordinate transform, and this actually is called like the naked singularities because you can actually get rid of them, but they are sensible objects, meaning that while passing through an event horizon of a black hole, you wouldn't actually experience something that is distinctive. But when you hit the singularity, imagining that of course you would be conscious at that time, because as you get closer to the singularity, the tidal forces would eventually become asymptotic, infinite. So you would actually die before reaching to the black hole, but reaching to the singularity. But imagining that you actually are conscious while hitting the singularity, you would actually experience something real. So it's not like something pseudo, like the Schwarzschild radius. So what I'm trying to say is that somehow those dispersive effects needs to overcome the gravitational effects, and we can actually encode dispersive effects to classical general relativity with some simple assumptions. And using the field theoretic calculations that were developed in 1980s, you can actually calculate some real phenomena and observe and make predictions about cosmology. So, but before that, where did we get the inspiration to introduce dispersion into the system? Well, dispersion was first, let's say, introduced to the systems by themselves. I mean, what I'm trying to say is that in a laboratory setting, when people wanted to create an analog of a black hole, what they did was to take Bose-Einstein condensates or an optical system. In an optical system or in a Bose-Einstein condensate, you can mimic the event horizon of a black hole and observe what we call as Hawking radiation, which is the emission of a black hole, radiative emission. So, but what people observe is that in those laboratory settings, there are always some malfunctions, there are always some dispersive effects. And people initially believed that those effects would actually distort what we needed to observe about Hawking radiation. But it was on the contrary. Those dispersive effects seems to be something so fundamental that actually Hawking radiation wouldn't be happening without those dispersive effects. So maybe those analog experiments are telling us something. Maybe they are telling us that space and time needs to be dispersive at the event horizon of a black hole. So think it like this. Normally, for example, in our solar system, since we don't have a black hole in our solar system, space and time can be thought of like this smooth page. But of course, as we get closer to the sun, this smooth page assumption that we make about space-time gets distorted. And this can be seen from the perihelion of the Mercury, a famous confirmation of general relativity. But if you get closer to a black hole, what would you see that this paper would actually look like a terrain near a volcano. Like when you walk, your feet start to hurt because of those stones, and they are so uncorrelated. They basically are the essence of the dispersive argument, because like humans, let's say 100 people are walking through this smooth manifold, smooth page. What would you observe is that if people, of course, arrange that everyone is walking in the same, let's say, direction, you would see that people will continue to move on that same direction. But when people are moving through that volcano terrain, because of those stones and everything, people will start to move in different directions after some time. And this is actually what we call as dispersion, as I explained to you. This is exactly what happens to light when it passes through a refractive medium. It basically distorts and gets into different places. It becomes chaotic, it gets a chaotic shape. Like distribution of people, the light ray also gets chaotic. Of course, assuming that light ray isn't a monochromatic light ray, but that's not important at this point. So this is the basic idea. Dispersion is central in our calculations.